The other really useful concept when it comes to curve sketching, symmetry. If you know the symmetry of the curve, then in effect, you only have to draw half of it, because then you can reflect it or rotate it depending on the symmetry that you've got. Odd functions. Odd functions. Formal definition. Function negative x is equal to negative function x. So if you have to prove something is odd, it's no good saying, oh, well, it looks like it is, or anything like. You have to prove that. Function negative x is equal to negative function x. Visually, point symmetry, or rotational symmetry about the origin. Parabola, is it odd? No. Hyperbola, is it odd? Yes. You could rotate that 180 degrees and get the same shape. Cubic, is it odd? Yes. Circle, is it? No. It's not a function. Can't be an odd function if it's not a function. Okay. But of course it does have nice rotational symmetry. Okay. So if you spin 180 degrees, it will look the same. Y equals x cubed. Y equals 1 on x. Y equals x to the 7 minus x to the 5 would be an odd function. In fact, minus 3x to the power of 9 plus 2x to the power of 7, that would be an odd function. When you're dealing with polynomials, it's getting real easy because all the powers are odd in an odd function. That works out nice. But again, that's not good enough for a proof. But if they haven't asked you to prove it and you just want to know, and you say, oh, look, all the powers are odd, I know it's an odd function. If all the powers are odd, so we've got a polynomial or any other continuous curve, and you know it's an odd function, what can you tell me with 100% certainty about the graph? A particular point on the graph must be there. Yeah. Because if it has rotational symmetry about the origin, it must pass through the origin. Remember I said continuous. Obviously the hyperbola, it doesn't, but that's not a continuous curve. If it's continuous and it's odd, 0, 0 must be on that curve. All right. So we're going to prove that x to the 3 plus x to the 7, yes, we look at it and go, oh, look, the powers are odd. I know it's odd, but that's not good enough. So let's find out. There's function x. Let's have a look at function negative x. Negative x cubed would be negative x cubed. And negative x to the power of 7 would be negative x to the power of 7. And that, in fact, is the negative of function x. So there's our proof. So it's the negative of the original function. So yes, that is an odd function. Even functions. That's where function negative x is equal to function x. Also has symmetry, but it has line symmetry. So the y-axis is the axis of symmetry. Parabola, is it even? Yes. Hyperbola? No. Obviously, because we just said it was odd. Cubic? No. Can we catch them twice? Circle? No. Very good. It's not a function. Examples. X squared. X squared plus 4. Hang on. Because the same thing applies. We say if all the powers are even, x squared plus 4. For the sake of this, we think of 0 as an even number. Is 0 an even number? There's a good question. Is 0 an even number? Define an even number for me. Okay, now we're doing real numbers with a factor of 2. Yeah, I think you might have got me on that one. That's good. Does that mean negative numbers can be even? Yeah. Certainly for the sake of this definition it can. If you had x to the power of negative 2, that would be an even function. So, all right. So yeah, all the powers are even. Let's go and prove x squared plus 4, just in case you don't believe me that 0 we're pretending is even. Function x is x squared plus 4. Function negative x would be negative x squared. Square negative x, you get positive x squared. Oh, look. That's the same as function x. Even function. All right. Told you that bit was going to be quick.